is Oleg, and I'm going to be talking about...
Hold on. You passed out sheets for me?
Yeah, we have sheets. First Joe did.
You were lavender didn't pass out.
Yeah, one of the two. Lavender says.
Yeah, there's still some left over here. We have some.
Really, dude? Like one in the sun and one hasn't.
This is mom.
What's your team color?
We're Orchid. Sorry about that. Alright, my name is Oleg Scottson. I'm going to be presenting on the duct cooling system. This is a previous system because we were actually assigned a new system a few days ago. My team members are Nathan Helton and Patrick Moss. Today we will be going over a little system background, the FOPDT theory. We will look at FOPDT models, results, and some conclusions. This is our system. It consists of air blower, 3 booths. For our input, for our system, the second damper was actually closed. And an interesting thing about our system is that we were actually cooling, so as input, as system input increased, the temperature for our system actually decreased, so it actually worked in the inverse direction. Here's a block diagram. For the input, we put the intensity that we wanted our motor to run at. The system was our duct cooling system, and as an output, we got a resulting temperature. Here's a sample constant flow operating curve. As you see, it took a few minutes to get up to the constant flow, and we had an average of 55 degrees Celsius with an uncertainty of 0.3 degrees. And we have arrows to clearly point out which is which. Here's a sample step function. This is actually a step down function, but as you can see, when the blower input went down, our temperature actually rose because it was now cooling at a less intense rate. And in this particular slide, we see that the time constant is equal to a minute. That's when the temperature rose to 63% of its entire rise. And that time was observed to be about 0.6 seconds. This is the same graph, but I left out the DC and the DM from the other slide because it'd be a little too crowded. And UC gain is DC divided by DM, which is equal to 0.2 degrees per percent. This is the FOPDT theory. We see the standard step function and response to the step function, where K is the gain and T is the dead time. Here's a FOPDT model. Again, we have arrows to show which is which. You see input, output, experimental input, and experimental output. Here's some results. We had a gain of 0.2 degrees Celsius per percent. As you saw earlier, dead time of 0.6 and a time constant of 1 minute. When we ran the model, our gain was 0.35 degrees Celsius with an uncertainty of 0.23 degrees Celsius per percent. Our dead time was 21 seconds as opposed to 0.6 seconds, which is an uncertainty of 31.6, and a time constant of 2 minutes, which was double our experimental time constant, which with an uncertainty of 1.55 minutes. And from this, I came up with a conclusion that if an alternate FOPDT model could be made up for an inverse system, I feel like the results may have been slightly closer. Are there any questions? Thank you.